In this video, we're going to be talking about the areas between curves. If you think back to Calculus 1, we mostly focused on derivatives, but right at the very end, when we introduced the concept of an integral, the way that we explained it was in the context of the area under a curve. So in Calculus 1, areas were related to integrals, and that's going to continue to be the case here in Calculus 2. So in Calculus 1, integrals were introduced in the context of areas under a curve. And when we talked about the area under a curve, what we meant was the area between the curve and the x-axis. So if you want to think about it, typically we worked in the first quadrant. We had a curve sitting up there, and we wanted to find the area from that curve down to the x-axis. In this case, our goal is to sort of broaden this so that we don't have to use the x-axis as our lower bound for the area that we're seeking. So that's what we mean when we say areas between curves. I want to have two curves, and I want to find the area in between them, and I don't want either of the curves to be the x-axis. So if you go back and recall what it looked like in Calculus 1, the picture that we had in that scenario was the following. We had our axes. Here's our x-axis, here's our y-axis, and say we wanted to find the area underneath. So let me write this here. If we want the area under y equals f of x, here's what that might look like. So we have our axes, and here's maybe some generic function that I'm going to say is our y equals f of x. There's our generic function. And maybe we want to find it between, so come back up here, let me modify this a little bit. I want the area of, the area underneath y equals f of x between x equals a and x equals b. So let me specify the bounds. And that means that maybe we have a starting point A right here and an ending point B right here. And the area that we're interested in is this area right here. Now I'm going to unshade that and think about how we actually computed that area. So I want to go back to sort of the definition of an integral and how we worked towards that definition when we first introduced the concept. And the first way we talked about finding areas under a curve was to break up the area under the curve into a bunch of rectangles and approximate the area under the curve. So let me do that here in this picture. If we break this up into a bunch of rectangles, and so here's the tops of my rectangles, and so on and so forth, we could find the area of all these individual rectangles, add them up, and get a pretty good approximation for the area under our curve. So the way that we did this approximation, I will write right beneath this here, was in the following way. So we said that the area was approximately equal to the sum of the areas of all of those rectangles. And the way that we found the areas of those rectangles is we picked a width that I'm going to call delta x, that's what we used there, and then we also found the height. So this was our width, delta x, this is our height, and the height, because it's the distance from the x-axis up to the function, the height itself is just f of x. So this f of x is equal to the height. And all we need is to be able to remember that the area of a rectangle is width times height, and we have our area of each of those individual rectangles. Then we just add them all up. So because we're dealing with a bunch of different rectangles, what we did is we said, okay, let's, instead of looking at one specific specific f of x, let's look at f of x sub I. And I'm going to put a star there and say that maybe the ith one of these or I is meant to be an index that can represent any one of those rectangles, and I'll come back to that in just a minute. So I took that for my height, delta x for my width, I multiplied them together as I've written here, and I've summed them up, and I'm going to sum them between I equals 1 and some bigger number, in this case n. I'm going to say there's n total rectangles. And in doing that, it means that the way our indexes work is that this first rectangle is meant to be I equals 1, the second one is I equals 2, and so on until we get to the end. This one's represented by I equals n. So when I is equal to 1, I pick some point. This f sub xi just needs to be any point. So here it is, right here. That point right there is my x sub I with the star. It doesn't matter if I pick a point on the left-hand side of this rectangle, on the right-hand side of this rectangle, or somewhere in between, because the height at all of those points is pretty similar. I'm going to get a decent approximation. That's all we're trying to do anyways right now, is come up with an approximation. So I can pick my x sub I to fall anywhere as long as it falls somewhere on that first rectangle. And then I do the same thing for my second one, any point in the second rectangle, and I use that to evaluate the height of my rectangle, and so on and so forth. So that's all this star is meant to indicate, is I don't care if I'm using the left point, the right point, it just needs to be some point somewhere on that ith rectangle, if that makes sense. Okay, so this is approximate. We're adding up a bunch of rectangles. If we wanted to make this exact, then we need to do the following. So let me write it right here. If I want to get an exact representation of the area, I need to use limits. I need to use more and more rectangles. The more rectangles we use here, the better the approximation that we're going to get. So I'm going to use a limit to let the number of rectangles, which we said is n up here, we're using n total rectangles, I'm going to let n go off to infinity. And so now we're going to use an infinite number of rectangles. That doesn't change much about our formula. We're still going to start from 1 and go up to n, but now n is just a really large number. And we're still going to pick a point f sub xi somewhere on that ith rectangle, and we're still going to use delta x. But I want to think about what happens to delta x as the number of rectangles that we're using increases. So delta x is supposed to be the width of one rectangle. But as we use more and more rectangles, each rectangle is going to get narrower and narrower and narrower so that they can all still fit between A and B. So there's some dependence that this delta x has on n itself. So I want to keep in mind that this happens where our delta x is going to get smaller. How exactly do we represent that delta x? Well, it's the width of one rectangle. How do I find the width of one rectangle? I need to find the width of the entire interval that I care about, which goes from A to B, and then I just need to divide that into n equal parts because I have n total rectangles, and that'll give me the width of one rectangle. So that's exactly what I'm going to do. I'm going to take the total width, which is b minus a, and then I just need to divide it by n, and you can see that there's an explicit dependence for our delta x on n, on the number of rectangles that we're using. What is this whole thing equivalent to? Well, it turns out this is our exact limit definition of the integral. So I can rewrite this as the integral from a to b of f of x dx. So there's a quick reminder of how we derived the concept of an integral back when we were doing this. The question that hopefully you're asking, or hopefully you already know the answer to, if not, if you don't need to ask it, is why does this represent an area? So why does the integral that we just computed, that we just derived, why does this represent an area? Represent an area. So I'm going to go through what each part of this integral means, what all these symbols mean when we write this out. So let me rewrite this. Here's my integral. I'm going to write it kind of large so we have some room to fill stuff in. Just recopying exactly what I've written right here. And I want to point out what each part does. The first part that we have on this left side is the integral symbol. And it basically looks like a stretched out letter S. If you took the letter S and stretched it vertically, this is the shape that you would get. And that's what it actually is meant to represent. When this symbol was first introduced, it was meant to represent the letter S for sum. All an integral is a big sum. We're just adding a bunch of stuff up. So the symbol says that it's a sum. We need to add a bunch of stuff up. These things are the bounds. They tell us when do we start adding, when do we stop adding. So the bounds tell us where to start and stop adding. So far, the integral symbol and the bounds just say add a bunch of stuff up, start here, end here. Whatever we add up is what we're going to get out of this whole thing. So we just said what we're getting out of the whole thing is an area. So that must mean that this stuff in here represents an area. If I'm taking a bunch of little areas and adding them up, I will just get a bigger area. And indeed, that's what the units wind up telling us. We just saw in our picture up here, this f of x, this is a height. This is just the height of the function. And dx is meant to be a little tiny piece of width. It's an infinitesimally small piece of width, but we're adding an infinite number of infinitely small things and getting a finite result out of it. So this is the idea. Between these two pieces, the height and the width, that's what gives us the area in this case. But it doesn't have to represent an area. This is just sort of the geometric picture. If I let f of x have some other meaning other than a height, and I let dx have some other meaning other than a width, other than a little piece of length, we could have f of x represent a rate, maybe a velocity, and instead of dx we could use dt. So we could have v of t be our function here, a velocity with respect to time, and dt would be little increments of time. And when I multiply a velocity times a little bit of time, what do we get out of that? So a velocity is sort of a rate. Rate times time gives us a distance, and we could compute a distance out of all of this. So really, whatever these two pieces wind up multiplying together, whatever units these two pieces give us, they're going to dictate the result of the entire integral. The units are really important. Units matter. And more than mattering, the units help. They make this problem easier as we continue to work on problems. In the next couple of sections, you'll see this in 6.2 and 6.3. We are going to be finding volumes. And the way that we're going to find volumes with integrals is by adding up a bunch of tiny volumes. And so we need to ensure that the formulas, or these pieces in the integrand, that they represent, when you multiply them together, a volume, so that we add them up and get a big volume out of it. So the units matter, and they're actually going to make the problems easier. They're going to make them make more sense. So I want to jump into a few examples and hopefully not inundate you with too much stuff here, but let's start with a fairly straightforward one. In fact, actually, before we jump to an example, let me do one other thing. What I didn't mention yet is we've talked so far about the area under a curve, but I mentioned we want to find the area between curves. So how do we find the area between curves? Then we'll do an example. So how does this all relate to the area between curves? Well, all we need to do is remember that y equals 0 is the equation of the x-axis. And so what we did when we found the area under the curve, between the curve and the x-axis, was essentially this. So our area that we just talked about was really equal to the integral from a to b. You can think of it as f of x, that was the curve that we had on top, minus 0. So I had a y equals f of x on top, I had a y equals 0 on bottom, and if I subtract the two, this gives me the area between y equals f of x and the x-axis. But what if instead of using y equals 0, what if we use some other function? Well, that's going to be the idea. In general, instead of using y equals 0, pick y equals some other function, some g of x for the lower bound. And now we can find the area as follows. Integral from a to b of f of x minus g of x dx. And this is the area below y equals f of x and above y equals g of x. But this has to be the top and this has to be the bottom. Otherwise, we're going to get a sign error in our result. So keep that in mind. Now we're ready to do some examples. And as we do this example, keep in mind what we've just found here. If I were to draw the shape, we'll do one in a minute, this still represents f of x minus g of x still represents a height, and this dx is still going to represent a width. We're now just measuring the height between the top of our shaded region and the bottom of our shaded region. It's the top minus the bottom, so to speak. So let's get back to this example. So in this problem, I want to look at a couple of curves and actually find an area. So let's put this to practice. So in this case, I want to find the area between the following. Let's see here. Let's find the area between y equals, let's say, 2 minus x squared and y equals x squared. And let's also do it between 2 points. Just delete this, x squared. Let me write it this way. From x equals 0 to x equals 1. So this is the idea. We want to find that particular area. So let me move that out of the way. The easiest way to start this problem is going to be to get a visualization of what's going on here. So I want to draw a picture of our two curves. In this case, it's going to look something like the following. So this is where it's going to be important for you to kind of review your graphs of at least some common functions. I'm not going to ask for graphs of arcsecant or anything like that, but basic ones. Polynomials, particularly parabolas, maybe some cubics, sine and cosine, exponentials, logs. Just know a few of the basic shapes. So in this case, I know that y equals x squared is a parabola, and it goes like this. And it also continues off in the other direction, but we don't care about that side because we're only going from x equals 0 up to, let's say that is x equals 1. And I know when I plug in x equals 1 into this equation, it's going to spit out y equals 1, so this must hit this point at a height of also 1. The other equation that we've got here also is a parabola because it's also a second power polynomial, but the negative sign here tells me that the parabola is flipped upside down, and the 2 that we've got here tells me that it's shifted up 2. So it must go through this point up here, and it is also a parabola, but it points down instead of up, and it continues on this way. And notice we don't care about the left-hand side, but if I just let these functions continue, they would also intersect at the point over here at a x value of -1. We just don't care about that in this particular case because we only care about the area from 0 to 1. So here is the area that we're trying to find. That is the shaded region. And it's clear that based on the way that we drew things, this function is the one that's on top, and this function is the one that's on the bottom. And so we need to use that as we plug into our formula. So to find this area, we know that our area is going to be equal to the integral from our starting point, which was 0, up to our ending point, which was 1, our two x values, of the top minus the bottom. And in this case, the top is going to be 2 minus x squared. There's our top equation, or our top function. And we're going to subtract off the bottom function, which is just x squared times dx. So this is what this particular area is going to look like, top minus the bottom, and that's what we're integrating. So we can simplify this, and we will get the integral from 0 to 1 of, in this case, that 2 is the only constant, so it's going to still remain a 2. But I have a minus x squared in the first term, and I'm going to have another minus x squared from the second term, so I'm going to wind up with a total of minus 2 x squareds dx. And I like to throw some parentheses around this to make it clear that we're integrating that whole thing. And so when we actually conduct our integral, let's evaluate our integral at this point. These ones are hopefully easy enough that you can remember how to do them. My approach for simple ones like this, especially when we're just going to be doing sort of a power rule, is you've got to remember that when you integrate, the power is going to go up by 1. So right now you can think of this as 2 times x to the 0th power. X to the 0th power being 1. Anything to the 0th power is 1. So this basically is something with a polynomial of order 0. When we integrate, it's going to go up to a first order polynomial. So the integral of this piece is just simply 2x. This other one's going to go up to an x cubed, so I know it's going to be an x cubed. But if it were just an x cubed and I were to take the derivative, I would get a 3x squared out of this. And I don't have a 3x squared, I have a negative 2x squared. So to make up for that, I need to put in a negative 2 thirds. If you have another approach that you prefer for your integration, if you just memorize the formulas, totally fine. But now when I take the derivative, the 3 would come down and cancel with this 3, and I'd be left with a negative 2x squared, which is exactly what we've got. So there's what the integral looks like. Now we just need to evaluate it between the endpoints, so from 0 to 1. And in doing that, I just need to plug in the function at the upper bound, so 2 times 1 minus 2 thirds times 1 squared. There's sort of the upper bound, and from that I'm going to subtract off the lower bound. This is just coming from the fundamental theorem of calculus. Back in Calc 1, the lower bound is 2 times 0 minus 2 thirds times 0 squared. That whole lower bound is going to evaluate out to 0. And so these are the two that are going to actually contribute. 2 times 1 is just 2. Negative 2 thirds times the 1 squared is just going to be negative 2 thirds. So I've just got 2 minus 2 thirds. If you do this with fractions, you can think of this as 6 thirds minus 2 thirds. The net result is 4 thirds. And there's our answer. So the area of this region is 4 thirds, a little bit more than 1. And just looking at our sketch, that seems totally feasible. If you looked at just half of it, so just a quick sanity check, if I cut it in half like that, and then imagine that if we continue down there, this area would have, that I'm drawing in blue, this area would be an area of 1. The red portion is clearly less than that, but it's more than half of that because it's more than cutting this thing in half diagonally. So I have a number that's greater than a half, but less than 1. Then we're doubling it, so I've got a number that's a little bit bigger than a half. We double it, and we get a number that's a little bit bigger than 1. So sanity check-wise, this number makes sense. Let's do another quick example, and I just want to maybe get the setup of this one for you so that I don't take up too much of your time. But what if I don't give you, like I did in this one, what if I don't give you the bounds of integration? If I don't give you, say, let's start at 0 and end at 1, how would we figure out where to start and stop if I don't give you those? If I just say find the area between these two curves. So let's see what I mean by that. So I want to find the area between, the first function I'm going to do is, let's do this one. Let's do y equals x squared minus 1 and y equals 2 minus 2x. And so again, if I start with a graph of this, I know it doesn't ask for a graph, it just asks for the area. But drawing a quick sketch almost always is going to help you sort these problems out. So that's what I'm going to do. I'm going to start with my sketch. So here is my x and my y-axis. This first function, y equals x squared minus 1, that's a parabola. It opens upward, but it's shifted down by 1. So I'm going to say it's down here. It's going to go through this point. Here is my, excuse my drawing. There's my parabola. So that one, maybe I should do it in a color. No, we'll just leave it black and white for now. So there is the first one. We've done that one. And the other one is a line. And this line has a y-intercept of 2 and a slope of negative 2. So it's going to start up here. So if this was negative 1, 2. What you can imagine is it's going to go through this point, and then it's going to go down at a slope of negative 2, means it's also going to go through this point. But it's going to continue on this way. Of course, I didn't leave myself enough room. So luckily, the magic of whiteboards, I can erase this and fill it in. So I'm going to extend this parabola up this way, extend this way, and you can see they intersect at this other point as well, over here. So find the area, and I cheated. So what is the area we're interested in? It's this entire region right there. We need to know that these two graphs intersect at two separate points. We want the area between those two graphs. So that means I'm interested in finding what is the x location of this point, and similarly this point. So these 2 points, the green points, let's do it in green. I need to know those x values. So that I can figure out what my bounds of integration should be. So how do I figure out, how do we know where they intersect? Well, we're going to do the way that we always find where two graphs intersect. They intersect where they have both the same x-coordinate and the same y-coordinate. So I've got expressions for what these equations look like in terms of y. If this one has a y value that looks like this in relation to x, and this one has a y value that looks like this in relation to the x, and I set these two y values equal to one another, as they must be at those 2 points, then we wind up with the following. So all we need to do is set the equations, equations equal to one another. So in this case, I'm going to set the first one, the y equals x squared minus 1. It must occur at the same y value, have the same height as this other one, 2 minus 2x. And at this point, we can move all of everything to one side. I'm going to move these 2 things over to that side. Undo that real quickly, and I'll wind up with x squared. I'm going to move this 2x over, so I need to add 2x to both sides. So x squared plus 2x. I've already got a negative 1 on the left. I need to subtract 2 from it, so it's going to be minus 3 equals 0. now I just need to solve this equation to figure out what x values we were looking for over here. What are those x values? So how do we do that? Well, this is a simple quadratic. We just can either use the quadratic formula or factoring. In this case, this one's pretty easy to factor. It's going to be x plus something times x plus something equals 0. We just need to figure out those two somethings. So I'm looking for two numbers that when I multiply them based on foiling, I get a -3, but when we add them, which is also based on our foiling out, we're going to get 2. So two numbers that multiply to -3 but add to +2. So that's going to be a +3 and a -1. We can just double check ourselves. We'd get x squared as we foil, plus a 3x minus x, there's my 2x. And a -1 times 3 gives me the -3 that we're looking for. And out of that, we wind up with figuring out that x is going to be equal to either 1, if this is the part we set equal to 0, or -3, if this is the point. Sorry, this is the one that we get set equal to 0. And so that's what we wind up with. And clearly here, my drawing's not to perfect scale, but we got one that occurs at 1, and this one must occur further over, and it turns out it occurs at -3. So there's our bounds. So when we set this up, I'm not going to compute the integral, but our integral is the following. It's going to be the integral from our starting point, -3, up to our ending point of 1, of the top minus the bottom. And so looking at this picture, which curve is on top and which is on bottom? The line is on top, so that's the 2 minus 2x. That's our top curve. Do this in parentheses. And then we're subtracting the bottom curve, which was the parabola, which is the x squared minus 1. So there is our top minus our bottom times dx. And if you go through and solve this, which I'm hoping all of you can do, when I did it, I got, let's see, I got about 10 2/3. If I write my mixed fractions here. So you can go ahead and give it a shot, check your answer. Hopefully I didn't screw that up, but that's what I wound up with. One other point that I really want to reinforce, and then I'll come back to maybe one or two other little ideas, is the following. So we really need to keep in mind that it must be top minus the bottom. So we need to know which one is on top and which one is on the bottom. And if we were looking at this, imagine I had a setup where here's one graph that we've got, it does something like this, and here's another one that I've got that does something like this. So if this is y equals f of x, and there's y equals g of x, and maybe this is my point A right here, and here's my point B right here, then the area that we're interested in is, if I want to say the area between the curves, I guess I should erase where I put that B, that was a bad location. So let me put the B there. I really have to treat it as two separate areas, area 1 and area 2. And in this region, and where area 1 is, the top curve, if I follow this one, so following the top curve, it is the f of x. So for area 1, in this case, this has the top is f of x, and the bottom is equal to g of x. But in the second region, that's reversed. And if I wasn't careful and didn't reverse it, if I just did f of x minus g of x all the way from A to B, what I'd find is I'd get a positive area for this region, but then here where f of x is below g of x, I would wind up getting a negative result, and we would be adding a negative area, which doesn't make sense. If I just want the area between the curves, I don't care who's on top and who's on bottom. I just want the the areas that I've drawn. So in this second case, for area 2, we need to keep in mind that the top is now g of x, and the bottom is f of x. And we would need to figure out at exactly what point right here that changes. So we need to figure out where the two curves intersect. Because for them to cross one another, they have to intersect with one another. And so what we really need to do is we would call maybe this point here C. I'm going to call it C. And so what we would do is for our total area, we would have two pieces. It's going to be A1 plus A2, but if you keep in mind how those two things are going to be found, A1 is going to be the integral from A to C, right? So I'm starting at A, ending at C, with f of x on top, so f of x minus g of x dx. That's the A1 term, plus the integral from C to B, which is the starting point and ending point of the blue shaded region. But in that region, g of x is on top, and f of x is on the bottom. So I have to reverse the role of those two pieces. So again, just to make it totally clear, that piece corresponds to that piece, corresponds to the blue shaded region. This piece corresponds to this piece, corresponds to the red shaded region up above. So just keep in mind, it helps to draw a picture. The picture will help you figure out where those intersections occur. Mathematically, to find out where those intersections occur, we need to set our f of x and our g of x equal to one another to figure out where those types of intersections occur. So keep that in mind. We may have to compute our total area, we may have to put multiple pieces together. One thing I do want to mention, just in passing, I'm not going to force you to do this much. The example we did a minute ago, it was nice when we set these two equations together, are equal to each other. We got a nice quadratic that was easy to solve, but that's not always going to happen. Sometimes we'll set two equations to get equal to one another, and we'll wind up trying to solve an equation that has no solution method that we can figure out with pen and paper. And in those cases, what you would have to do is approximate things. So you'd have to use a calculator, use Desmos, some sort of graphing utility, to come up with an approximate point of intersection. At the end of the day, you're going to realize this more and more. There are a lot of problems that cannot be solved with pen and paper and have to be approximated, so approximately solved computationally. And that's just one example. Let me sneak in maybe two other quick topics, just that might help you with stuff that might come up on the homework. If you want to approximate things, so these are just more examples. So approximations. What if I gave you a shape that looked like this? And I wanted to find the area. And I told you that maybe we could split this up into a couple chunks. Hopefully those are, well, I can do a little better than that. Let me draw these a little more evenly spaced. Let's say it looks like that, just to make things easy. And I told you that this distance from here to here, this distance from here to here, this distance from here to here, if I give you those distances, maybe this one's a distance of 4, so height of 4, maybe this one's also 4, and maybe this one's a little less, it's 3. And if you think about these endpoints over here, you can think about it as an arrow going like this, but it really has a height of 0. And same thing over here, sort of a height of 0. And if I also tell you that as we measure these things this direction, and this direction, and this direction, and this direction, the widths of all of these, let's say there may be 2 each. So 2 meters, 2 meters, 2 meters, 2 meters, and maybe these are also all done in meters. Well, how would you approximate the area of that particular region? And the answer is, it depends. We can use rectangles. So we could use the left endpoints of all of these to try to come up with our approximation. And if I did the left endpoints for my heights, I'd get a rectangle of height 0 here and width 2. For the second one, it'd be a height of 4 and width 2, and it would go to there, basically. The next one would go here. And the last one would go basically like this. And it looks like it's not a great approximation, but it's something. We can also do the same thing on the other side and use the right endpoints instead of the left endpoints, and we could get a similar approximation. But let's just do one of them for now. So these are using the left endpoints. So using the left endpoints, I wind up with a bunch of rectangles that I'm adding up. The first one has an area of 0, so the height of each one is 0, and the width is 2 in this case, and that gives me an area of 0. So the next rectangle has I'm just going to separate these lists with maybe commas. The next one has a height of 4, a width of 2, and that gives me an area of 8. The next one after that also had another height of 4. So where am I getting these? Again, all I'm doing is keeping track of these heights. So there's the first height was 0, so I can totally clear this. This 0 went with this 0. Let's get some more colors here. This 4 goes with this 4. This 4 goes with this 4. So I'm just going across the list, picking up heights. Let's do one last one. Let's make it purple, and it'll be the one that I write right here. That last height is a height of 3. All the widths were the same. They were all 2. And I'm just multiplying these two numbers together to get this number down here. So this one will also be 8, and this one will be 6. And I add up the areas of each of those rectangles, and if I add them up, 8 plus 8 plus 6 plus that 0, 8 plus 8 is 16, plus 6 more is 22. And we need to keep in mind the meters squared are the units that we've got, because we multiplied heights, which had units of meters, with widths that had units of meters. So we're not just multiplying the numbers, we're also multiplying the units. Meters times meters gives me square meters, or meters squared, however you want to write it. So keep that in mind. You could do the same thing with the right endpoints. You could do a bunch of stuff like that. So just keep this type of thing in mind. You may see a problem like this on the homework. Let me do one last example and let you guys go, or one last topic really. There's going to be some situations, and we're going to see these in the upcoming sections, where it's more convenient to integrate with, let me write it out loud, with respect to the y-axis. Instead of integrating along the x-axis and having all our little rectangles be oriented vertically like they were in this picture, sometimes it's going to be more convenient to orient them horizontally. And we'll see examples of that over the next couple of sections. So let me just mention real quickly how we would think about that. So this is going to come up in the following situation. If the bounding curves of the area that we're trying to find, so of our area, if they're more readily expressed or more easily expressed in the reverse, so instead of y equals f of x, if it's as x equals f of y and x equals g of y, with points y equals c and y equals d being bound in the vertical direction, so sort of our starting and stopping point, the things that played the role of a and b in our initial integral. If that's the case, and if our f of y is bigger than our g of y, so one last thing. So f of y is uniformly larger than g of y. If all of this is true, then our area is going to be equal to the integral from, say, c to d of, in this case, f of y minus g of y dy. And this looks crazy and it's hard to remember until we just, again, draw a picture. So just draw the picture and you'll see what I mean. So in this case, maybe this is what our picture looks like. Here's the x-axis. Here's the y-axis. For whatever reason, the curves that we're dealing with are more easily expressed in the following way. Maybe here's what those curves look like. And this is the, let me write this clearly. This one is the x equals f of y, and this one over here is the x equals g of y. And clearly, this x value is always, so this curve is always to the right of this curve, meaning f of y is always a larger x value, spits out a larger x value than the g of y. So that's this condition right here. And I guess it can be greater than or equal to. So as long as we've got one curve that's always to the right, therefore has larger x coordinates than the one to the left, then all we're doing is finding our area this way. Here is some point C, here's some point D, and we're slicing this thing up this way. And this now represents the height, and these represent a width. And the width is basically we're taking a bunch of rectangles that now look like this, right? We're slicing it up this way instead. Same idea as what we did before, then taking our limit. But that's all this is. The width is now we take the larger value, the larger x value, subtract off the smaller x value to get our width. And then dy is a little tiny bit of height in this direction. And now we're just adding up a bunch of rectangles that are oriented horizontally instead of being oriented vertically. So again, this is what our little dy is. It's a little bit of height in this case. So keep this idea in mind. It's going to help us a lot in the next couple of sections.